Hi again everyone, Chris Tisdell here again. In this presentation I'm going to continue my series of videos on complex numbers. Now in previous presentations we talked about various forms of a complex number, including a polar exponential form. Now in this video I'm going to do an example that draws on various aspects of that polar exponential form. So let me share my screen with you and we can start. Okay, so we're given two complex numbers, Z and W. And we're asked to do a few things. We're asked to compute the product ZW in Cartesian form, rewrite Z and W in a polar exponential form and calculate the product in polar exponential form, and hence determine a precise value for the tan of pi on 12, or the tan of 15 degrees. Okay, so let me just refresh your memory. This is a polar exponential form of a complex number. R is a length known as the modulus of Z, and it's basically you plot Z in the complex plane, and R is the distance from that point to the origin, and theta is an angle to the positive real axis. Okay, so let's work out part A first. This is a pretty easy part A. Compute Z times W in Cartesian form. Okay, so all we would do is write down the two Cartesian forms and expand them, remembering that I squared equals -1. Okay, so let's expand that. So you're going to get -2 times 1 and 2i times -i root 3. So if I group the real terms together and get 2 out of that, I'm going to get 2 root 3 times -i squared. So that'll be positive 1. So I'll get 2 root 3 there. And what about the other parts? Well, 2i times -1 and -2 times -i root 3. So if I write those out, I'll get this. That's going to be 2 root 3, and I've factored out the I. Okay, so that was pretty easy, right? Now, the second bit gets a little bit trickier. Rewrite Z and W in a polar exponential form, and then calculate the product in polar exponential form. So to do this, what I'm going to do, well, it's always good to draw a picture or a diagram. Okay, so here is the Argand diagram, or the complex plane. Let's plot Z and W and see if that simplifies our transition to their a polar exponential form for them. Okay, so for Z, I've got -2 here plus 2i, so I go 2 units that way and 2 units that way. So maybe up here. Okay, so that might be where my Z is. And for W, it's -1 minus I times root 3. So I go 1 unit this way and root 3 units down here. So I'd go sort of out there and then say down there. Okay, so that would be my W. All right, well, if I join some line segments from those points to the origin, then what I'm interested in is calculating the two lengths and the angle to the positive real axis. Okay, so what I can do if I want to, I mean, you may be able to look at that and go, okay, well, I know the answer already. What I can do is I can actually just draw a couple of right-angled triangles associated with these complex numbers. Okay, so let's think about Z first. The base is 2, the height is 2, so by Pythagoras, that squared plus that squared equals the hypotenuse squared, so that's root 8 will be the length. So that's just 2 root 2. And the angle in here, well, that can be computed using trigonometry. But I mean, you may see that, okay, well, this length and this length are the same, and it's a right angle triangle. So this length, this angle has to be pi on 4 radians. Okay, so that little angle there will be pi on 4. So the angle to the positive real axis will be 3 pi on 4. What about W? Well, if I draw another right angle triangle associated with W, this length here is going to be root 3. The base is going to be root 1, again using Pythagoras if you want to. The hypotenuse will be 2. And then using trig, this angle here is going to be pi on 6. Okay, or 30 degrees. Okay, so if that little angle in there is pi on 6, the angle from the positive real axis is going to be pi on 2 plus pi on 6. So that's going to be negative 2 pi on 3 because we're rotating the other way. We're rotating clockwise, whereas up here we were rotating anti-clockwise. Okay, so from our diagrams, we have a polar exponential form of z. Z is just this length, 2 root 2 times e to the I theta, where theta is the angle to the positive real axis. Well, if that's pi on 4, that will be 3 pi on 4. And similarly with W, W is 2 units from the origin and going this way, pi on 2 plus pi on 6, that'll be negative 2 pi on 3 because we're rotating in a clockwise direction. Okay, so from these two forms we can now quickly multiply them. So the product is just this, and we just use our power or index laws if you like. Okay, so it's going to be 2 root 2 times 2, so it's going to be 4 root 2, and you just add the exponents if you like. So if I add 3 pi I on 4, 3 pi I on 4 minus 2 pi I on 3, I'll get the following, e to the pi I on 12. So that's part 1. Part A, this is part B. Now I know that A and B are the same product, right? So this and this will be equal. Okay, so this now gives us the opening for part C. All right, so let's work with part C now. If I say plot this or this in the complex plane, then they're the same complex number, and I know that, okay, well, to plot the product, I'll go this far out in this direction and this far out in this direction. So it'll be about here, I reckon. Okay, so that is 2 plus 2 root 3. And this is basically 2 root 3 minus 2, all times I. And so you get a little triangle, another right angle triangle here, where this angle here is pi on 12. Okay, so you basically have a little right angle triangle in here now. And you can just, you know that because of this form, the angle's got to be pi on 2. Because of this form, the side, the base and the height have got to have this length and this length. So you know that the tan of this is just opposite over adjacent, right? Tan pi on 12 equals opposite over adjacent. So this over this. Okay, now you can see that we can simplify here. You can scrub off the 2's. So I'll get something like this. Okay, so that then is an exact value for tan of pi on 2 or tan of 15 degrees. Now, if you want to put this, get rid of the square root sign down here, you would say multiply by the conjugate of this, so to speak. So you could multiply, say, by root 3 minus 1 over root 3 minus 1, or 1 minus root 3 over 1 minus root 3. And if you do that, you'll get 2 minus root 3. Okay, so you can, I guess you can take that one if you're satisfied with that, or we can go another step further and go down here. Okay, so that is a good example because it uses a lot of ideas that we've discussed in previous videos, especially these polar exponential forms and just, you know, a bit of geometry and a bit of visually geometric intuition as well, which is kind of nice. Okay. Now there are perhaps simpler ways to get this, but this is you know, a video on complex numbers, so this is the way it's going to go. Okay, so that's my presentation. Thank you for watching. Hope it was helpful. If you have any comments or any questions, you can always post a comment in the comment section. If you have any suggestions, then I'd love to hear them. Thanks for watching. Hope you can join me for more presentations in the future, where I'll continue my series of videos on complex numbers. Bye.